Alright, welcome back to Rock the JVM. I'm Daniel, and in this video I'm going to talk about variance positions in Scala. Now, this video assumes that you're quite familiar with Scala generics because the problem that we are going to discuss is quite cryptic, and the problem that we're going to solve here is a compiler error that doesn't say too much unless you understand the concepts really well. And the compiler error says something like covariant type occurs in contravariant position. Now, this kind of compiler error bugs even some of the advanced Scala developers, so this video will be quite valuable. Now, as always, I'll recommend that you code with me in this video because I'm going to prove everything that I'm going to state step by step and in real code. And whenever you need to refresh your memory about these concepts, and I'm going to warn you this video will be quite dense, just refer back to this video or to its written form at the blog with the link in the description. I'm also going to mention that what you're about to watch I also teach in the advanced Scala course over at Rock the JVM, so if you're curious about it, go ahead and check it out. I also will add a link for your convenience. Now, if you're ready, just hit a thumbs up and let's get started. So I have a new class here. I'm going to make it an object just in case we need to test anything. This is a plain Scala 2 project. The concepts that I'm going to talk about are also available in Scala 3 exactly as I'm going to discuss them here with zero syntax changes. So this video will be quite timeless for you guys. So here's what I'm going to do. I'm going to describe variance in Scala because it's one of the most powerful concepts of its type system. And it's very simple in theory, but it can cause pretty massive headaches when we think we got the hang of writing abstract and generic code. And in this video, we will take a careful and structured look at one of the most cryptic compiler errors that you will ever see. And we won't need a particular project setup, just a plain Scala project will do. So this video will assume that you're familiar with generics, either in Scala or in other statically typed languages like Java or something like that. And beyond the capability of the Java generics, Scala also has the concept of variance, which is a way of transferring subtype relationships from the type arguments to the generic type. Now, this sounds quite complicated until we bring it back to real life. So imagine we're having a small class hierarchy, like a class animal and a class dog, which extends animal, and a class cat, which extends animal. And just for the fun of it, let's do a class crocodile extends animal. Okay, so we have a small type hierarchy over here. Now, let's assume that we're implementing a generic collection, which I'm going to call my list. So I'm going to create an abstract class or class. I'm going to call this my list, and I'm going to add a type argument t here. So if we have this small class hierarchy, which is pretty canonical for demonstrating object-oriented inheritance, then it makes sense to ask the following question. If dogs extend animals, so if dogs are animals, then is a mylist dog also a mylist animal? So in other words, if a dog is an animal, then is a listed dog also a list of animals? This is called the variance question. And in more general terms, if you define a class or a trait which is generic in a type argument, this variance question is relevant. And there are a bunch of answers that you can give to this question. And option number one is to say yes. If dogs are animals, then a mylist of dogs is also a mylist of animals. If we answer yes to the variance question, then that means that the generic type is covariant. And we mark covariance with a plus sign over here next to the generic type argument to the class. If you have a covariant type, then you can then say, if I define val, let's call this animals as a mylist of type animal, then on the right hand side, I can write new mylist of type dog, for example. Because you can also say val an animal of type animal equals new dog. So for the same reasons that we use in object orientation, we have a proper substitution between a dog and an animal, in the sense that we can assign a dog to an animal because a dog is a subtype of animal. And because a dog is a subtype of animal, we can replace this animal with a dog. And in the same style, we can replace a list of animal with a list of dogs. So the answer yes to the variance question attached to a generic type means that that generic type is covariant and we can do this. There are a bunch of other possibilities, and I'm going to answer no. And if the answer is no, then the generic type is invariant. And invariance means that my list animal has absolutely no subtype relationship to my list of dog. So they are completely separate types and you cannot substitute one for another. And if that is the case, then invariance is marked by the absence of any sign here next to the type argument t. And once I remove it, notice that the compiler starts to complain because the right-hand side says my list of dog and the left-hand side says my list of animal, and the compiler is unhappy with that. Now, a third answer, because there's also a third answer, is hell no. And actually backwards. In other words, if dogs are animals, then your generic type of dog is a supertype of a generic type of animal. Now, this may sound a little counterintuitive, and this is called a contravariant type. So I'm going to say generic type is contravariant. And for the animal-dog kind of relationship, a good use case for contravariance is a vet, which can heal animals. So if I define a class called vet with a negative sign, this is how we mark contravariance. Then if I define a value called, let's call this Lassie's vet, which is a vet of dog, because it can hear our beloved Lassie, is on the right-hand side a new vet of animal. So notice that the subtype relationship is actually backwards. We can substitute a vet of animal for a vet of dog. And this is a legal replacement because if you think about it, we require a vet of dog, but on the right-hand side, we provide a vet of animal, which can heal any animal, including our dog. So this is a better kind of vet. So I think you get the idea, and if you want to know a very compressed version of how to choose variants for your generic type, I actually tweeted about it, and I also tweet very, very, very smart things there at the Twitter Rock the JVM channel, so you can check us out there. Now, because we've just found that a collection should be covariant, and if you want to define your own collection and you get to work on it, we can write something like this. I'm going to define another class. Let's call this myList2 because I don't want to mess up with the types. So I'm going to make it covariant because we've just learned about it, and I'm going to add a bunch of methods. So I'm going to define a head, which returns a t. I'm going to define a tail, which returns a myList_t, or myList2t, and I'm going to define a method called add, which adds an element of type t and returns a new myList. So I'm going to return myList2 of t. I'm going to make it an abstract class because I don't want to implement these right off the bat. I just want to define some method signatures, and this would pose the variance problem. Because if you've paid attention, notice that the compiler is unhappy with my add method, which is basically the fundamental method of a list. We can add elements to a list and return other lists. But if you hover over this error over here, the compiler goes back to you with a very cryptic text. Covariant type t occurs in contravariant position in type t of value element. What the hell does that mean? Even as we just learned about covariance, we apparently don't know squat. So we are going to take a very structured approach to why this kind of error occurs and how we can get around it. So in this video, if you have another 15-20 minutes to spare, I promise you this will be a good investment of your time. So I'm going to comment out this code, and I'm going to get back to it a little bit later. And I'm going to start with the very beginning. And I'm going to start with the types of val fields. And let's say we had a vet class like this, which is contravariant. I'm going to define a class, let's call this vet2, so that we don't have any conflict with the previous vet. So I'm going to define a vet2 with a negative sign because we've just learned about how to make it contravariant. By the way, we also have a video on contravariance here on the Rock the JVM channel, which I really recommend you check out if you are confused about why would we ever need contravariance and why that will be useful. So I'm going to define a class which is contravariant, and I'm going to add a val field to this class, and I'm going to pass it as an argument. So I'm going to say val, let's call this favorite animal, and I'm going to make this animal a t. Now, this is the first kind of error that you are going to see by the compiler that seems like the one I just described. and we see contravariant type T occurs in covariant position in type T of value favorite animal. Again, what the hell does that mean? And we are going to explain what it means. This first use case is one of the simplest. So here goes. Assuming this kind of declaration was possible, and I'm going to comment this out, then we would be able to write something like this. I'm going to define a value called Garfield, which is a famous cat. So I'm going to create a new cat, and I'm going to create a vet. I'm going to call this the vet, and actually, let me uncomment this back just to show you how that will work. So the vet is a vet2 of animal. And on the right-hand side, I'm going to create a vet2 of animal. So I'm going to say new vet2 of animal, and I'm going to pass Garfield. All right, because the vet2 receives a val field as type T. And Garfield, being a cat, is also an animal, so I can pass it around. Now, because of the contravariance property of vet, I can say something like line 23 here. So I can define, let's call this Lassie's vet2 as type vet2 of dog. I would be able to say the vet on the right-hand side, because the vet is a vet2 animal, and so it's a better vet because it can treat any animal and therefore my dog as well. Now I'm going to ask you, what kind of type will Lassie be if I do Lassie's vet2 dot favorite animal? What type does Lassie have? And the answer is a little bit ambivalent, because Lassie's vet2 is declared as a vet2 of dog, and so the favorite animal should be of type dog. However, this vet2 was instantiated with Garfield as argument, and so the actual type of favorite animal is going to be a cat, not a dog. So we have a type conflict, which the type checker will never allow in the first place. And so it will say that this val field is in a covariant position. So a contravariant type, such as a vet, cannot have a val field of type T. So I'm going to comment this out and the subsequent code with it. Now, if the generic type was covariant, for example, if it was a list, then it would work. And if the generic type was invariant, then we wouldn't even have this problem, because we would have the exact same animal type everywhere. All right. So the types of val fields are in covariant position. Now, what about variable fields? So I'm going to bring this code over here, and I'm going to define a class, let's call this vet3, with a field of type var. Now, if the field was of type var, it wouldn't change the previous scenario at all, because we would have the exact same situation. So it doesn't really matter if the field is val or var. So we have types of var fields are also in covariant position. I'm going to comment this code again. Now let's try a generic covariant type. Let's see if that works. So imagine that for whatever reason, we had a mutable version of an option. So I'm going to define a class. Let's call this mutable option. I'm going to make it covariant, because an option is kind of like a list, and we talked about earlier that lists are covariant. And I'm going to define a class mutable option, which is covariant in the type T and has a variable member. I'm going to have it contents as type T. But notice this time we have another compiler error saying that covariant type T occurs in contravariant position in type T of value content. So basically the other way around. So we have types of var fields are also in a contravariant position. So look at that. So we have covariant type T occurs in contravariant position, even though this field is also a variable. Now, why is that? I'm going to define a small use case that will prove that. So let's define a value, let's call this maybe animal, as maybe or mutable option of animal. And on the right hand side, I'm going to define a new mutable option with dog, and I'm going to use new dog inside. Now, because this field here is reassignable, I'm going to say maybe animal dot contents equals new cat, because contents is of type animal, and so I can replace that with a new cat. But obviously this breaks some type guarantees, because on the right hand side here we have a mutable option containing a dog, so we need to somehow guarantee that this mutable option will only contain dogs, but in line 46 here we are replacing that with a new cat, and that is because we have a variable field of type t, and so we have another type conflict. And so we have the fact that the types of var fields are also in contravariant position. So not only in covariant, but also in contravariant position. The only way that a var field would work with a generic type t is if the generic type was completely invariant, because you would have the same type everywhere. All right. So variable fields do not work with variance with generics. So I hope these make sense. We're essentially proving the compiler errors by trying to find a counterexample that would induce a type conflict. So we demonstrated the types of val fields and the types of var fields and which kind of positions they are. The next scenario that I'm going to talk about is the type of method arguments. And the problem of the type of method arguments is the very common problem when you want to define a covariant collection and you can't really add elements to it. So I'm going to cut this code and I'm going to paste it here. This is the exact scenario that I'm going to talk about now. So we have an abstract class that I'm going to call mylist2. I'm actually going to remove the first two methods. I'm only going to concentrate on this one, which has an argument of type t. Now again, for the sake of argument, let's imagine that this code compiled. Let's also imagine that we gave some dummy implementation to this method so that we can actually instantiate the class. I'm going to make it non-abstract and I'm going to pass a dummy implementation. If this was the case, and if this code compiled, then I would be able to say the following. I'm going to define a value called animals2 as my list2 of type animal. And on the right hand side, I'm going to create a my list of a derived type. So I'm going to create a new my list2 of type cat, for example. Now, because this value is of type my list of animal, I can add an animal to it. So let's call this more animals. Let's call this more animals2 to be consistent with the to notation here. I'm going to add animals2 dot add, and I'm going to add an animal, for example, a new dog. Is this legal? Well, it's not, because the argument here is of type animal, which is theoretically in accordance with the declared type of this value, but because on the right-hand side we declared it as a my list of cat, we imply that this list contains just cats, and yet we're adding a dog here. So we have a type mismatch, or a type conflict. So in other words, we say in a more formal way that the type of method arguments are in contravariant position, because a covariant type cannot coexist with a method that takes an element of type t as an argument because of this situation over here. So I'm going to comment all this code, and I'm going to demonstrate a use case with a contravariant type having a method like this. So if you had a class, let's call this vet3 with a negative sign, if you had a method which takes a value of type t as an argument, for example, heal animal as a type t, and this say returns a boolean, and let's say the implementation returns true, the implementation is really not that important, then this is perfectly legal, because if you wanted to define a vet, let's say Lassie's vet3 as type vet dog, and on the right hand side we provide a better vet, which is in our case a vet of animal, so a new vet3 of animal, and let me put the 3 here as well. Then I could say Lassie's vet3.heal. The heal method takes an argument of type dog, and so this is perfectly valid. If I do Lassie, for example, or a new dog. So this is perfectly legal, and if I said Lassie's vet3 heal new cat, then this would be an error, and this would be a legitimate error this time around, because the heal method takes an argument of the same type as the vet was declared with, which is of type dog. So this is a legit error. I'm going to comment this out. All right. So for a contravariant type to have a method taking an argument of type t, this is valid. Now, the final thing that I'm going to talk to you about is method return types. And for this reason, I'm going to define another form of a vet just because I want to keep the code a little bit cleaner. So I'm going to define a vet4 with a negative t over here. And instead of the method heal, I'm going to define a method called, let's say, rescue animal. Having no arguments and returning a t, I'm going to leave it unimplemented because I'm going to make it an abstract class. So I have a new abstract class and named it vet4. It is contravariant and it has a method that returns a type t. Now we're gonna have a very similar compiler error saying contravariant type t occurs in covariant position in type t of value rescue animal, and I'm going to prove why. So let's assume that this code compiled. We're going to resort to the similar reduction ad absurdum kind of logical method. So I'm going to define a vet as a vet4 animal. And I'm actually going to implement a vet4 animal. So I'm going to say new vet4 animal, where the implementation of rescue animal is going to be a new animal. And in particular, I'm going to use a new cat. So this is supposed to return an animal because it's the same type with which vet4 was defined with. And I'm going to return a new cat because a cat is an animal, right? So this makes sense. I'm going to name this vet4. Cool. Now, having defined this vet4, I'm going to run the exact same kind of Lassie's vet scenario that we described earlier. So I'm going to define Lassie's vet. I'm going to name this Lassie's vet4 as a vet4 of dog. And per the contravariance property, I'm going to use this vet4 on the right-hand side. Okay, so this is okay because vet4 is a vet animal. A vet animal is a better kind of a vet dog because it can treat any animals and therefore it can treat our dog too. This is kind of the logical reasoning behind the contravariance. Cool. Now, having defined vet4 as a vet4 dog, let's obtain a rescue dog. So I'm going to define val rescued dog, which is a dog, because I'm going to invoke the rescue animal method on this Lassie's vet4 instance. So I'm going to say Lassie's vet4 dot rescue animal. Now, what kind of type is this going to be? Well, it's declared as a type dog, and the rescue animal is supposed to return a value of type dog because rescue animal returns the same kind of value that it was defined with. So it's going to return a type t with which the vet4 was declared, in our case, a dog. So we should obtain a dog, but by the construction of this vet4 instance, we actually return a cat. So we get a type conflict again. And because we get a type conflict, the capacity to define a method returning a type t in a contravariant type is not allowed. And in other words, more formally, method return types are in covariant position. Namely, they cannot be used with contravariant types like this vet4 thing. So I'm going to comment this code and I'm going to place it just like that. So these are the kinds of variance problems that you are going to encounter while you define your own variance added data structures. So we discussed the compiler problems and why those arise. Now, in particular, we proved that a covariant list cannot really have a method that adds an element of type t and returns a list of type t. Does that ever forbid us from ever adding an element to a list? Hell no. So let's take this back to first principles and let's try to solve this problem and get around the compiler. So we said that we cannot really add an element of type t to a list because otherwise we would be able to write something like a list of animal is a list of something, like a list of cats, and then we can add a dog to it. Now, if you go back to real life, just imagine 3 cats and a dog in front of you. How would you call the group of those 4 things? Well, they will be animals, because this is the most specific type that describes all 4. You have 3 cats and a dog, they're all animals. So what if our add method over here received an argument of a different generic type? So if you added a different generic type argument here to add, have an element be a type S, for example, so something of a different type, and return a list of a different type. Allow me to make a small suggestion. So I'm going to define a class. I'm going to call myListC. That is myListCorrect or myListCovariant or something like that. And I'm going to make it covariant in type T. And I'm going to define an add method that in this case will have another type argument S, which is a supertype of T. So this has a lower bound in T, and I'm going to explain how that actually works. And the element that this method receives is of type S, and the end result is myListS. And I'm going to say new myListS, for example. I can do that. So how would that work? In other words, if you happen to read this method, if we happen to add an element of a different type than the original list of type T, then we will let the compiler infer the lowest type S, which describes correctly both the element being added and all the elements that are already in the list. And as a result, we obtain a new myListS. So in our case with the cats and dogs example, if you add a cat to a list of dogs, we'll obtain a list of animals because a cat is an animal and the compiler will infer that the S type is an animal. If you add a flower to a list of animals, you'll obtain a list of something bigger, like a life form. And if you add a number to them, you'll obtain a list of any. And you get the idea. So basically, we're widening the type of the returned list. And this is how we solve the cryptic covariant type T occurs in contravariant position, because you may notice that the compiler doesn't really complain about it any longer. And similarly, we can solve the opposite contravariant type T occurs in covariant position with the opposite type bound. So if you added an abstract class, let's call this vet or vet contravariant with a negative T, and if I wanted to define a rescue animal, we would make this return not type T, but some other type S that I'm going to add as a generic type argument. So I'm going to add another generic type argument S, which in this case is an upper bound with T. So this would be an extension of T. So notice that this is quite the opposite of what we did earlier with the covariant list. And this is now valid because the compiler doesn't complain about it any longer. And assuming that we can actually implement this method in such general terms, the compiler will actually be happy because we can force the vet to return an instance of a particular type that we like. So if I want to say val Lassie's vet, I'm going to have Lassie's vet C as a vet C of dog, and on the right hand side I'm going to say new vet C of animal. And in order to make the code compile, I'm actually going to make this class non-abstract, and I'm going to return some question marks over here to make the compiler leave me alone. And if I do val rescued dog, dog C, just to add the right suffix here, this can be a dog, and I can say Lassie's vet C dot rescue animal. And this would actually be inferred by the compiler to say rescue animal with the type argument dog, as inferred by the compiler. So we can make the compiler infer the right type S to return here, assuming we can actually implement this method. So this is how we can solve the variance problem. If you have a covariant type and you want to process an element, you would process an element of a different type, which is a supertype of T. And if you have a contravariant type and if you want to return a value of type T, you don't actually return type T, but a type S, which is different and is upper bounded in T. Now, this is one of the hardest parts of the Scala type system, this variance problem, even though it starts from such an innocent question, but I hope these examples proved useful. So if you want to go back and recap the lessons that we learned in this video, the video was quite dense. So we started with a variance question, which was quite innocent in its nature. So if A is a subtype of B, then for your generic type thing should think of A be a subtype of thing B. This is the question upon which you decide what variance you should add to your generic type thing. And the variance possibilities are yes, which is covariant for the example of lists and collections. You can choose no, which is invariant, and that means that thing A and thing B are completely separate types with no type relationship between them, and hell no, being the thing B should be a subtype of thing A with the example of a vet in our code. And after exploring how variance works, we discovered variance positions, and we discovered the kind of type checks that the compiler will automatically make in the case of a generic type with variance. So that means that the type of val fields are in covariant position. That means that only covariant types work with val fields. Types of vars are in covariant and contravariant position, meaning that no variance will work with variable fields other than invariant. Then we have the types of method arguments, which are in contravariant position, meaning that only contravariant types can have methods taking the elements in the type argument that they're defined with. And method return types are in covariant position, meaning that only covariant types can return the type that they're defined with. And if you want, you can try to prove these so-called theorems or properties yourself by following the examples that we went through in this video. And if you want to actually solve these combinations, for example, if you want to have a covariant data structure plus a method that takes an argument of type T that the generic type was defined with, then you need to widen the type, add another generic type argument, we call that S, which is a supertype of your initial generic type, and vice versa with the other combination with a contravariant data structure with a method that returns the type that the data structure was defined with. So if you took these lessons to heart, that will make you a badass Scala developer, and I hope this video was useful in helping you do that. In which case, you can click the like button for me and subscribe to the Rock the JVM channel for more videos like this, and follow me on LinkedIn and Twitter for fresh updates on upcoming material. I'm dying for feedback as always, so leave your comments, I read every single one, and check out the Rock the JVM website and the Scala Advanced course, which teaches a lot of awesome stuff, including what you saw in this video. Until next time, I'm Daniel, signing off.